Yeah, so this is the third lecture indeed. Again, the slides are on my homepage if you want to download them. Yeah, okay, sorry. Let me go to this we covered yesterday. So today we start this Schauder estimate. Actually, yeah, when I gave the abstract, it was last year, and I thought that already for the conference in November of last year, we would have maybe a draft on yeah, okay, so a preprint on these Schauder estimates. Now, 1 year later, in fact, the preprint is not yet on the archive. It's not that we got stuck. It's just that we did something else. Actually, I don't know what else, but time flies. And so a couple of months ago, I started to panic about this event. Yeah, at the point, so I asked so Luca Brewer to join the project in order to revive it. So indeed, this talk is based on work in progress with Luca Brewer and Francesco Caravenna again. So a tentative title is Schauder estimates without regularity structures. So again, as for the reconstruction theorem, we have extracted one theorem essentially from the larger theory of regularity structure with the aim of presenting this in a maybe simpler and probably more general setting, okay? Without, again, without really defining regularity structure. We don't really need that. Yeah, a second disclaimer. So I wrote the second half of the slides for today, this night, between 3 and 6 a.m. So I didn't have really time to read it a second time. So let's see what, there should be no big problem, but we'll see. So yeah, let me remind you of what we did yesterday. So we defined the notion of coherent germs. This is a given, so RD space, a family of distributions indexed by the point space in RD, and so the family is in the distributions on RD, such that you have this bound for a fixed choice of alpha and gamma, where so they are real and alpha is less than gamma, essentially. Well, let's say maybe strictly less than gamma. And here phi is a test function, lambda is positive, and you define the scaled version of the test function phi in this way. So we discussed yesterday the fact that this notion is useful because it allows to obtain this result. This is the reconstruction theorem. Under this assumption, there exists a single distribution in RD such that for all x, so Rf minus Fx is essentially small close to x, and this is a more precise statement, a more quantitative statement. When you test against a generic now test function psi with the correct scaling, you get something which is bounded by lambda to the gamma. For gamma equal to 0, there is a log correction, and you have uniqueness if and only if gamma is positive. Okay. Okay. So now let's we discussed also this. We realized that in fact the space of germs is probably much too large. And so the idea in it's not very comfortable. Sorry, 1 second. Maybe it's better now. Okay. In fact, the idea in regularity structures and actually also in rough paths, so indeed the idea came first in rough paths and then was generalized by Martin, is to find a suitable subspace of germs where you can find probably the solution to the equation that you are studying. So in fact, this space, so this suitable subspace is defined in the following way. You have to find, to fix a finite family of germs, which has at least 2 properties, maybe more, but so for every x in Rd, you have this homogeneity beta I, which means this, that again, when you test pi xi, so in a function scaled around x, you have a bound with lambda to the beta I, where beta I could be positive or negative. So this again is called homogeneity, and there exists a. So if you consider now pi as a kind of basis at x for the distributions that you want to consider, then you need a notion of change of basis. In particular, when you move from the base point x to the base point y, and for that you need this matrix valued function, which satisfies this. So I said already yesterday that in regularity structures you have additional properties, but they are not necessary for us at this stage. For today, I don't need to assume anything more, and that's practical because essentially I only have two assumptions and not more. So indeed, the pair pi gamma, if it satisfies additional properties, oh, sorry, I forgot to, maybe the computer wants to feel some electricity. But that's kind of strange. I don't remember. Was it yesterday? Here. I was saying that in the regularity structures, the pair is called a model if it satisfies additional properties. So let us use also this terminology. So in any case, we already said yesterday that the terminology is bad, so it cannot get much worse if you call pi gamma a model. A second element that we discussed yesterday was the fact that for a fixed pi gamma, we can want to consider functions f from Rd to Rn with this property. So you see that only the gamma actually appears. And also there is the exponent small gamma, which is greater than all beta i's. And again, so in regularity structures, this is called the bounded distribution. So we also use that terminology. And we saw yesterday that the germ that you can define in this way, so if pi I comes from a model and fi is a model distribution with respect to that model, then this is a coherent germ. which, again, shows what I said yesterday a couple of times at least, that you see the semi-lemma and the reconstruction theorem in the version that we have given with Francesco are a very general, are two very general results which are not based on particular structures, but you can give to these two results, you can feed them with many different objects, and usually, at least this is what I know, the germs that you can, to which you can apply the reconstruction theorem are constructed in this way. And for the semi-lemma, we did not really see for the rough path, there is a similar notion that we did not discuss yesterday. It is the notion of controlled path. Okay, and so you fix a model, you fix a model distribution, you have this F, you apply the reconstruction theorem, and you define now U equal to R of F, which is now locally well approximated by Fx. Let's at least think of gamma positive. In this way, this is unique. But in fact, this is not really necessary. What I say in the following holds also for gamma negative. Now, let me introduce a new notation. You see, so the reconstruction is the reconstruction of capital F, but in fact, I prefer to think of this as the reconstruction of the model distribution small f. Okay, so I make clear that there is a model behind. I write here pi, but in fact, what I mean is that I reconstruct this object, which is therefore the sum of pi I fi. So maybe I write this on the blackboard. So yeah, so yeah, R pi f is in fact R no R of sum where I pi I f I. Okay, I will use this notation. Yes, please. Yeah, exactly. Yes, I had this computation yesterday. Yeah. Please. You mean? No. I would say that this is really a sufficient condition, but it is stronger than, so it's much stronger than what is needed to have coherence. Yes. So indeed, yeah, okay, thanks. This allows maybe a small digression. Yeah, so when we did the first paper with Francesco, then we were very happy. We thought maybe we can really get rid of regularity structures and do everything just with germs. But there is one point which cannot be treated without a kind of a structure of this kind. It's products. So this I will discuss tomorrow, in fact. I will show that if you have this structure, so if, in particular, if your germ has this structure, then you can, this is Martin's idea again, handle a notion of product of model distributions. In general, you take two germs, there's no way, so you cannot multiply them. So, okay, so that's much too general, much too big as a space. Yeah, so in fact, thanks. Products should come rather tomorrow, but it is a nice detail to discuss. Okay. Now, yesterday, we said that one example of models is this one. Okay, so remember that pi is supposed to be a distribution. In this case, this is a function, a smooth function of w. It's just a standard monomial. Then the gamma is given by the Newton binomial theorem. And in this case, a model distribution, this we didn't say yesterday, actually, if you apply the definition, satisfies this, okay? Now, a question, what does this remind you of? Yes, a Taylor expression. So what, in which setting are we here? What is Fi? I give a hint here. So in fact, if you have you see I have a function from Rd to Rn. So here Rn actually is all, you have to count how many multi-indices with norm less than gamma you have. In fact, so the point is that there is F0, so with the zero index, which is equal to the reconstruction of this model distribution, and all the other components are partial derivatives of u. Okay, so if you apply this to f, so I equal to 0, here you have all the other components which appear, and this is possible only if these components are equal to the derivatives because of Taylor expansion. Okay, so at least, okay, let's say that gamma is different from n, because otherwise, you know, the Taylor expansion is okay. Here I'm considering gamma not an integer. Yeah, so in fact, this is a very important point. So model distributions are essentially families of derivatives of some, okay, maybe the reconstruction. So in the generalized setting, this is a bit maybe less clear, but so at least it is a nice interpretation. So if you go back to the general case, for a fixed model, we denote by d gamma, and if we want, we can specify the model, d gamma of pi gamma, the space of all model distributions, which means modeled by the model. If we take this case of monomials and Hölder functions as a source of inspiration, then we can interpret model distributions as collections of generalized derivatives of the reconstruction with respect to the model. Okay? So they contain information on our object. So in principle, you should always think of U as your solution to the SPD or whatever, and as the model distribution. So yeah, U is the solution. Pi is a family of objects which you have fixed. And F is a family of coefficients which allow to describe U on the basis of pi. Okay? So in fact, you have access, so you have very strong information on F, and U comes as a corollary in a sense, but it is on small f that you will be working on. So you remember, so the definition of f was that this was bounded by this. So you take semi-norms. So it is d gamma which becomes your Banach or Frechet space where you set your equation. Now the original thing is that this depends on pi gamma, okay? And for example, for SDs and SPDs, pi gamma is usually random. So in fact, your equation is set in a random, say, Banach space or Frechet space, which is somewhat different from what usually is done in ODEs or PDEs, okay? But it turns out to be a very convenient way. So you are constructing, as I said before, you don't have the whole world of germs. You choose, okay, it will be relatively large anyway, it will be infinite dimensional, but it will be already prepared to contain your solution if you do things correct. Okay, yes? Yeah, sorry, I forgot the I, yes, of course. Okay. Okay, now this is, okay, I am not really speaking much about equations, so Ilya told you more about that yesterday. So this is, again, a bit the general strategy. So in this now space of model distributions, we want to set an equation in the form of a fixed point. So you will have to construct lambda, which is a map from d gamma to d gamma, non-linear map, and you will look for a fixed point like that. So then you define the reconstruction of f, which again is a distribution. And in principle, I told you, U is the solution. So you would like to think that U is also solution to a fixed point problem, U equal to lambda tilde U. Again, think of 5, 4, 3. So everything which Ilya said yesterday was in this context, okay? And here you see the relation between these two formula is that if you take the, this should be R pi probably, so if you take the reconstruction here, okay, you get U, and the right you get the reconstruction of lambda should be lambda tilde of the reconstruction of F. So in principle you expect this kind of commutation, okay? But the problem is that, in fact, so lambda tilde is not really defined. If you take reconstructions of your model distributions, you don't get a proper Banach or Frechet space. So in fact, this is not really working, at least our present knowledge does not know how to handle this. So this is what we can handle. So this is really mathematically perfectly defined. So while U remains now a distribution and there are all these renormalization problems of the products, etc. In a sense, we have lost the equation for U, or to be more precise, we have lifted the equation to d gamma, so to F, and now the equation is this one. It's not this one. Okay, so I don't know whether this is perhaps strange or disappointing, but we have such a good control of this that we should not really feel too sad about that, okay? Because on this we really have a complete theory, while this remains a kind of mysterious object. Okay. Now, for example, I mentioned again this phi for D equation. So you remember Ilya told you this is essentially a parabolic equation where you have, this is the mild formulation. So G is the heat kernel, P is some polynomial, which can, okay, for phi 4D, it's a cubic polynomial. Xi is some noise, but let's say, some external force, some fixed distribution. So you see that to handle, so this would be lambda tilde, okay? So then you want to lift this to a function, a map lambda in this framework. Okay, so I'm showing you lambda tilde. In fact, you want to construct lambda. And then you understand that you need at least two ingredients. Okay, the sum is not difficult because model distributions form a linear space. But here we have an integration of model distributions with respect to a kernel. Here, this would be the heat kernel. And a product of model distributions, which is important because of the polynomial here. Otherwise, if you don't have the polynomial, the equation is linear and it is much easier. So the difficulty comes from the fact that you have product. Yeah, so today I want to concentrate on the integration, which, with respect to a kernel, which is the motivation for this Schauder estimate. Okay, and now, as I said before, tomorrow I'm planning to discuss products. Right? Questions? Okay. So the integration kernel, so is a function that we fix here. Okay, this is not the most general situation that we can consider, but just for simplicity, consider a function k from Rd to R, which has this property. So for some eta positive, this function and a certain number of its derivatives, okay, and the number of derivatives depends on the exponents of the problem, has to be bounded by this power of x. So, notice that in principle this is a negative, so there is a singularity at 0 possibly, and okay, again by simplicity I take a compactly supported kernel because the problems at infinity are not relevant here. So if, for example, you can think actually in the proofs you reduce your most of the time to k to a series, a sum over n, and you can think of something like that. So eta appears, this parameter eta positive appears here. So epsilon n is 2 to the minus n. You have a series epsilon n to the eta times L rescaled at scale epsilon n for a fixed test function L. Okay, so again, I'm showing you this for two reasons. One is that it's very important to, again, in proofs, to decompose k as a sum of kn, this would be kn, functions which will be smooth. So for every n, this will be smooth. Then you, in order to see the role of eta, and again, so in the rest of the talk, this will be hidden, but in the proofs, that plays an important role. Okay. So if you take the green function and you multiply it by the indicator function of being in a ball or radius 1, then this is true with eta equal to 2. Okay, you have and eta is the regularization parameter. So as you will see in a second, so not parameter. I mean, the kernel regularizes by 2 for the heat equation, and in this general case, the kernel regularizes by eta. Okay, so now, what do we want to do? Suppose we have a model pi gamma, a model distribution f in d gamma pi gamma. Again, let's take gamma positive, although this is not strictly necessary, and U, which is the reconstruction of f. So we want to define K convolution U. Okay, this should be a distribution, and this is what we, in a sense, it's at the level of distributions. This is the operator. It's just convolution with K. But now we want to lift this operation to model distributions. So in order to do that, somewhat the idea is that the K is going to transform also the model. So the basis will be transformed. There will be a new basis, a new model pi bar gamma bar, a new model distribution G in D gamma plus eta pi bar gamma bar. So this is in red in order to stress that it is very important. So this is the effect of the regularization. If you think of Schauder functions, you go from gamma Schauder to gamma plus eta Schauder. And now, the idea is that G will be the family of generalized derivatives of your integrated distribution, okay, with respect to the new model pi bar gamma bar. Now you see, so this is R pi bar because it's the new model. So again, I think it's really clear what one wants to do. So you want to integrate U against K. You have a model distribution which describes U. You want a new model distribution which describes K convolution U. And now we are just moving the structure that you have for U. You are moving it to a structure for kappa convolution U, which means you are moving your basis and your family of derivatives. Okay. So this is, after all, not so, maybe not so difficult, but okay, it's non-trivial. You will see there is some work to be done. But at least I think the picture is clear. So again, this is the plan. Yes, please. Okay, it was this, I took inspiration from the Schauder function. So I said that if the model is given only by monomials, then a model distribution is the collection of partial derivatives of the reconstruction. Okay, and so it's like the famous Gubinelli derivative. Okay, so Massimiliano does not want this to be called a Gubinelli derivative, but so this expression has remained. It is a generalized notion of derivative. It is a coefficient which multiplies a generalized Taylor expansion. Okay, it is only an interpretation, but I think it's useful. Okay, so in other words, we want to define an operator kappa, okay, calligraphic K from D gamma pi gamma to D gamma plus eta pi bar gamma bar, which sends so the model distribution F to the model distribution G, and then this will give this commutation. Okay, the reconstruction of the operator is the convolution between the fixed kernel and the reconstruction respect to pi, which reminds you of lambda and lambda tilde. Okay, so this is going in that direction. So this commutation between lambda and lambda tilde and the reconstruction is essentially this is the step at the level of the integration map. Yes, yes. No, K is fixed. No. So the integration kernel is like, yeah, it's like the heat equation, because again, you have one equation and you construct your space, which is tailor-made for that equation. Yeah, exactly. And then what changes is actually also the model is changed. So okay, thanks. The model contains the randomness. Okay, so you have fixed your space-time white noise, whatever, and this goes in the construction of the model. And then you have this space of germs which should contain the solution. Yeah, and in some sense, all parameters are already fixed. You don't have additional choices. So let me say that, for example, if you read Martin's paper, you have the same. So here you have pi gamma. Okay. So because of course in the end you want a fixed point, so you need to act on the same space. So pedagogically, I think this is easier to understand, because indeed Martin, in his section 5, has an additional theorem, which is called the Extension Theorem, which says that if you have a model, okay, then you can extend the model in such a way that essentially pi bar gamma bar is equal to pi gamma. So in fact, he also has this problem, but he does not express it like that. So it seems to me today that this is a bit simpler. And then you have a second step which consists in doing in such a way that, in fact, the basis is invariant under this property. So that, yeah, but that's not difficult. Okay. By the way, K is also clearly linear but continuous. So this is another important aspect, because when you do fixed points, then you need a contraction. So continuity is an important aspect. Okay, so again, you really, it's like for PDEs, where when you want to solve some heat equation with nonlinearities, you need all this, and we are setting the same structure on a space which is a bit more complicated, but in the end the structure is not so different. Okay. Now we should construct this new model. Now, in a sense, it is clear that the new basis, P bar, so pi bar, is supposed to contain germs which look like the convolution between K and the pi I. Okay. However, so this could be your first guess, but unfortunately this may not work, because you expect to have this property. Okay, it is natural to suppose that the homogeneity is shifted by eta, and then you want this property. But in fact, as soon as beta I plus eta is strictly positive, then that means in particular that this has to be small when lambda is small. But if you look, so in particular, if you look at this expression, so again, this is a distribution, say maybe it could be a function. If it is a function, then this has to be small, close to x. But there is no reason why that should be true. Why should K convolution with pi be small, close to x? In general, that's absolutely not true. It is whatever it wants to be. And in fact, yeah, this I wrote here. We have to modify a little bit. So this is the starting guess, but it is not the end of the story. In fact, it is natural to allow the new basis to be equal to k convolution pi plus or minus a polynomial. Okay. So why? Because polynomials are given by nature. Okay. So why the basis depends on the randomness, etc. So the pi I depend on the randomness, as we said, etc. But polynomials are always available. They are deterministic. They are okay. We can use them without problem. And so, in fact, yes, yeah. Well, because it works then. So. Because this is meant to be a kind of generalized monomial. So again, if you think of the case of the Schauder functions, that is just done with polynomials. And okay, in a sense, one possible answer is that this setting is always included in what we are doing. Okay, we want to expand that. We don't want to avoid it. Okay, so really, Schauder functions are always good for us. We want possibly to add other functions, but really, monomials and polynomials and Schauder functions are always in our structure. So that means in particular that the pi i's can also be monomials. This is possible. But even if pi I is a monomial, when you integrate again k, it will not be small around x. And so you will do the same, you see. So, yeah. Then, in fact, it turns out that if you, again, allow a polynomial here, then the choice of the polynomial is almost obliged. So you will have to subtract the Taylor expansion of, so you consider this as a function of zeta, so x is fixed. And then you subtract the Taylor expansion of this function at x. So centered at x. And then, at least in the smooth case, it is clear that you will have the correct bound. In the general case, so again, this is the situation where you have functions and you can compute at some point zeta. Otherwise, you need to interpret this as a distribution. Yeah, okay. So this will come in Ilya's talk. So there is behind an algebraic structure, but this is what, in fact, we call rather the positive renormalization, which is not meant to avoid divergences. It is meant to make something small. So this should be small at the correct scale. But indeed, so this uses a kind of Kohn-Kreimer algebra. So again, there is certainly an analogy, although this is not the renormalization step, which is also needed. This comes in a second part. Yeah. So also, I think this expression is one of the biggest problems or this expression is one of the biggest problems in regularity structure. It is something that people always find hard to digest. But after all, I don't know, you get used to it, and really it works, I think. So, and again, so Ilya will say, I think, something about it. Yeah. So now we need a technical lemma. So, I mean, we need a number of results, but this is one which I state for once, almost precisely. So if you have a fixed distribution and a point, suppose that at this point you have this kind of bound. Okay, so when you scale your test function, this is bounded by epsilon to the beta times the CR norm of phi. Then, okay, all the following objects are well defined, which is not trivial in general, because you see K convolution phi is, I'm sorry. Okay, I am, you see. Okay, I'm sorry. When you take convolution between a smooth function and here the integration kernel, I don't remember. Is this necessarily smooth, or I think we do have to decompose K, as I said, as a series of Kn. Okay, I'm sorry. Now, as I told you, this is still yes, here it's, yeah, okay, then this is trivial, thank you. So this is well defined. Okay, this is probably a bit more delicate, because you do not treat this as a distribution, you want to compute it at X. Okay, so this requires a bit of an argument, but it works, and it turns out that so you have the bound which you want. So indeed, you go from epsilon to the beta to epsilon to the beta plus eta. Okay, this is the crucial technical say improvement of okay. And notice that in fact when beta plus eta is negative, then here you're not summing a polynomial, you just have this, but still the result is true. So you have improved your C zeta is positive, you have improved your scaling, your homogeneity. Okay. So okay, there are several arguments of this kind which you need to do. And again, so until now everything was a bit how can I say, more on the algebraic side. This gives you a flavor of the analytical estimates which are behind. And okay, this is telling you that indeed pi bar I x has homogeneity beta I plus eta. Okay, so this is good. So this means that your new basis is doing the correct thing at the level of the homogeneities. Okay. Now, question, is this enough? So you should remember that we also need to build the new change of basis metric, so gamma bar, from which, okay, we have no choice but to start from gamma. So it is very simple to see that if you integrate pi j against k, okay, you integrate, so in fact, don't forget that the gammas are just real numbers, so the convolution hits only the pi, not the gamma. So the property of the pi's goes directly to the k convolution pi's. However, what about the polynomial terms? So at this stage, the polynomial terms annoy us slightly. Okay, again, so this is the definition, because if you compute what this quantity is, so then you get, you don't get zero. You get a contribution which is there and which you cannot eliminate. We have to take care of this right-hand side. But the good point, at least, is that this is a polynomial in zeta, okay, of degree at most gamma plus eta. And then it is enough to add to our basis pi bar the monomials of degree up to gamma plus eta. I already said before that monomials anyway are available in nature, so they are free, okay? They are I don't know, open source, and you can always install them in your regularity structure, okay? And indeed, so this means that our new basis will be indexed by a set lambda, which is this, so the indices of the previous basis plus the monomials up to degree gamma plus eta, where now P, it should not be a hat, it should be a bar. So pi bar is pi if I is in the previous indices, or it's just the standard monomial in the new indices, okay? Of course, the homogeneity of the standard monomial is classical. It's just absolute value of I. But now you have to define the corresponding gamma bar using this big expression on the right-hand side of this. So now the result is that. So yeah, sorry about that. So again, this should be a bar, not a hat. If you come from the previous basis, you put just ij, so gamma ij. If I and j are from the previous basis, this is gamma ij. If I and j are monomials, then this is the binomial coefficient. So you see what I mean. If j is in the old, so this is the term which takes care of that big right-hand side. So if j is in the old basis and I is in the new monomials, then this is the coefficient, and it's zero otherwise. Okay, so there's nothing special. It's just again, okay, one has to be a little bit careful because these quantities are in principle distributions that you want to compute at x, okay, but, and this also you want to compute at y, but you prove that this is correct under the assumptions we made on k. Yes? I didn't assume that. No. Yeah, no, okay, say if the pi's are linear independent, then it is a consequence. But in principle, at this stage, it is not necessary to assume that. No, suppose that the pi's are all zero, for example, then the gammas are arbitrary, you see. Yeah, exactly. What I'm saying, if the pi's are linearly independent at x and y, then the gammas will be, yeah. Yes? It's a sum over, yeah, you say it's beta A. The A is such that beta A is greater than that, okay? Because I had used the I, J, K, so I was running short of indices. Now, we wanted to define a new model and a new distribution with this property, okay? Namely, blah, 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 you remember. So we have constructed the model. We need to construct G. So in fact, now I am just throwing this at you. So this is the correct definition. Again, this is what Martin does, although probably if you check his statement, you will not recognize this, but it's the same. And indeed, it works. So you see, again, you have Gi is equal to Fi if I is in the old basis, and otherwise it is something which depends on the reconstruction of F minus this, blah, blah, blah. Okay, if you are in the monomial basis. And then, so this is the multi-level Schauder estimate, so theorem in the original paper by Martin, and now we are doing this kind of slightly more general version, and I think more pedagogical version. But it's like for the reconstruction theorem, it is really somewhat a more general result, maybe a bit less than for the reconstruction theorem, but it has its value, we think. So with the above definitions, it is true that G is in the gamma plus eta. This also has to be checked. The map defined in this way, okay? F is mapped to G, is linear and continuous in the norms of these spaces. And you have that commutational relation that I was hoping, okay, to obtain, that the reconstruction of G, which is Kf, is equal to the convolution between the singular kernel and the reconstruction of F. Okay, so yeah, questions? I am almost done. Questions? Yes, Tom? Yeah. Maybe yeah. Yeah. We have not reached that point yet of our work. Just to give you an example, the gammas in Martin's theory are supposed to be triangular with respect to the homogeneity, blah, blah, blah. This does not appear here. We don't need that. We don't need that gamma ij, so is 1 if I is equal to j. So you remember, all these properties do not appear. So I expect at some point that they are useful at least, or necessary, but I don't know yet. I'm waiting for that moment, or maybe it will not come. So yeah, because 99% of the times Martin is right, but maybe they will not. Again, I'm open to surprises. Maybe we can reduce a little bit, as I was. My aim is to lighten a little bit the theory, to present, to distillate it and present it in the easiest possible version, but without losing the power. You see, of course, if I give you a simpler result, but then which does not allow to recover the fixed point, for example, that's not useful. That's not a useful game. So now the game is to retain the properties which are necessary for the construction of the fixed point, but with less structure. Okay. Okay. So I'm done, and tomorrow we'll discuss products. Thank you very much for your attention.
Questions or comments? I would have a question. You use translation invariance strongly in.
Yeah, no, in fact, no. You
could, yeah, yes. The kernel you could.
You can have k of x, y. Yeah. You just need some additional assumptions. But,
my question is, can you generalize this to a manifold?
Probably, I don't know. Maybe. Anyway, so k does not need to be translation invalid. That was just a simpler setting. Yeah, exactly. Yeah, so anyway, these are local objects, so I guess also on a manifold this could be done, maybe. Yeah, but so the pi x could also be 0 outside a ball. So you see, you really need it only close to x. Then the gamma has to, yeah. Yes, Marcus.
Go back 2 or 3 slides where you defined pi bar. Yes. So in the first case, why is it equal to pi?
Sorry, no.
K convolution?
No, of course. No, that's the convolution. Yeah, you see. This was maybe 5 a.m. So, yeah, thank you. We correct this.